delay on the spike timing between the plasticity or STP. Very quickly, I'm going to talk about STP itself, its conventional form without delay. So then I'm going to talk about the analytic and simulation results. So what's STP? STP is a mechanism that modifies the synaptic strength based on the relative timing of the spikes. For example, if you have such a configuration of two neurons that are bidirectionally connected to each other, there is a synapse from neuron 1 to neuron 2 with synaptic strength G21. And there's a synapse from neuron 2 to neuron 1 with synaptic strength G12. For example, if you stand on the synapse G21, what you can see that the neuron 1 fires at time T1, which is less than T2. And you can see that neuron 2 fires at time T2. The ICTP says that if the presynaptic neuron fires first, so this connection should be potentiated. Okay, for the upper synapse, the neuron 1 is presynaptic neuron and neuron 2 is postsynaptic. So this connection should be potentiated, and the reverse connection obviously should be reversed. The effective time that the synapse can see is delta t, which is t post minus t pre. In this case, for the upper synapse is t2 minus t1, and for lower synapse is t1 minus t2. This is the typical profile of this CDP. The change of the synaptic strength is proportional to an exponential function. So whenever delta t is positive, and delta g is positive, and we have potentiation. And whenever delta t is negative, delta g is negative, and we have depression. So what's the problem? The problem is the conventional STP without any delay says that there cannot be both potentiation or both depression of both synapses. Okay. For example, from this schematic figure, you can see that without delay, assuming the green and red lines are the spiking type of neurons, the arrows show the exact time of spiking on each synapse. You can see that in conventional STP always, for example, for synapse 1 to 2, the presynaptic firing always preceding the postsynaptic firing. So the synapse 1 to 2 always should be potentiated, and the reverse connection should be depressed. So we cannot have bidirectional connection in this configuration. So conventional STP acts as a loop eliminating mechanism. What I'm going to show you in a minute is that if we add delay to the problem, we can show that we can preserve both connections. So if we add the delay to the problem, now the effective time that the synapse, for example, G21 can see is no longer delta t. For example, the synapse G21 can see that neuron 1 fires at time t, but the effective time that the synapse G21 can see is t1 plus the delay time of the axonal delay of the neuron 1. And the same holds for the neuron 2. So there could be different situations based on the time lag between the spiking of the two neurons. For example, if we assume that neurons are nearly in phase, so these are neurons, these are the spiking of neurons with delay. So we can see that we can use the delay to change the ordering of the spikes. Okay, so there could be three different conditions based on the numerical value of axonal and dendritic delays. For example, for this nearly in phase situation, in condition 3, when the dendritic delay is larger than the axonal delay, you can see that in the first synapse, neuron 1 to neuron 2, which neuron 1 is a presynaptic neuron and neuron 2 is a postsynaptic neuron, you can see that there always is a potentiation delta t plus. Okay? And also there is a depression, but because the potentiation time is much smaller than the depression time, the potentiation will be dominant. So this connection should be potentiated. And the reverse connection ordering of the sparks has changed because of delay. So we have potentiation also in the reverse connection. The same condition holds for nearly in antiphase situation, but this condition is somehow different. You can see that again we have potentiation and depression and again potentiation. We just consider the nearest neighbor interaction in this model. So again the potentiation time is much more smaller than the depression time, so we have potentiation again. And it's the same for reverse connection. So in simulation, for example, if you consider neurons that obey the Huxley model, which is a type 2 oscillator, that means in the slope of the PRC of the neuron, in the period of the neuron, in the middle of the period, it is in antiphase state, and in the first part and the last part, it's in phase state. So if we fix the interactive delay at 0.5 milliseconds, we change the axonal delay from 0 up to period of the firing of the Huxley neuron, which is based on the parameters, but in this case it's about 16 milliseconds. So the blue lines are the time lag between two neurons. It also shows the slope of the PRC of the type 2 oscillator. So we can see that when the neurons are nearly in phase situation, there is a potentiation of both synapses. The green and red lines are the final synaptic strengths of the neurons. But when the neurons are nearly in phase, because the condition for nearly in phase potentiation was large dendritic delay. So we don't have large dendritic delay because it's very small. So there is no potentiation here. If we change the model to Langevin-Sacchi model, which is a type 1 oscillator, that means in its period, in the first part, it's in antiphase state, and the second part is in phase state. So we can again see that when we are in phase state, there is also a potentiation of both synapses again. And when we are in phase state, there is no potentiation due to the conditions. So the conventional ICTP acts as an eliminating mechanism. By applying the delay to the problem, we can show that far more than the conventional outcome of ICTP, we can change the outcome of the ICTP and preserve both connection by potentiation. This preservation of connections depends on the time lag between two neurons, axonal delay, interactive delay, and the slope of the PRC of two neurons. The next step, we can construct a neural network and see what happens when we add delay to the system, what happens to the structure and dynamics of the system. Okay. That was it. Thank you.
So there is an underlying hypothesis that these characteristic effects of STDP are preserved when you have IFI effects.
IFI effects, yeah.
Yes. You have just a summation.
Rate-based model. Preserve connection in that situation.
So your hypothesis is that given the delay between the connections, you can break this asymmetry of SGP.
Yes.
My question is now, in the experiments like B and Bo that you have this dual clamping,
Yeah.
shouldn't you see also then points with a negative time scale that have potentiation, or with a positive that have depression? I mean, you need to have delays that are comparable with the time windows of STDP, and that should be apparent in the plots of STDP, which are quite noisy on the vertical scale, but they usually don't have like points in the wrong quadrant.
I don't know. All I'm saying that based on the numerical value directionally and energetically, and the position where neurons are, for example, nearly in phase and nearly antiphase is same. There could be potentiation of those synapses, not necessarily. We just wanted to show that this conventional outcome of plasticity can be changed. Good.